this video, we're going to be talking about graphing motion. So we've already learned about speed and distance and displacement, so let's review what we've learned first. First of all, if we want to find speed or velocity, we're going to use, for speed, constant speed. The average speed is equal to, the total distance all over the total time. For constant average velocity, we're going to put an average over there with a little arrow to denote that this is a vector. It's going to be the displacement all over the time. And then for acceleration, it is your change in velocity all over your change in time, or your final velocity minus your initial velocity all over the total time. And remember that velocity and displacement are both vectors, and that anything going to the east is positive, anything going to the west is negative, anything going north is positive, and anything going to the south is negative. We also talked about ticker tapes. We said if you're traveling at constant velocity or speed, your ticker tape is going to be dots that are consistently spaced, equally spaced. The further apart, the faster, the closer, the slower. And for acceleration, you would be speeding up to the right if your dots get further apart to the right, and you would be speeding up to the left if the dots get further apart to the left. So acceleration to the right and acceleration to the left. So if you are moving to the right and your acceleration is to the right, you'll speed up. Likewise, if you're moving to the left and your acceleration is to the left, you'll speed up. But if you're moving to the left and your acceleration is to the left, you're moving to the right and your acceleration is the opposite direction, or vice versa, the end result will be that you slow down. All right, now let's talk about graphing in general. Remember that when you graph, if you make a graph, you'll have an X and a Y axis. They will have their own I'm at a loss of words. Scale. And so let's say that this is distance in meters, and this is time in seconds. If you make a graph and it's linear, the generic formula of a linear graph is y equals mx plus b, where m is the slope, which is equal to, you pick any 2 points on that graph, and you find the rise over the run, or the change in y all over the change in x, which is y2 minus y1 all over x2 minus x1. So our x1 would be 2 seconds and 7 meters, and our x2 would be 5 seconds and 16 meters. So the slope on this graph would be equal to 16 meters minus 7 meters all over 5 seconds minus 2 seconds, which would be 9 meters divided by 3 seconds, or 6 meters per second. So the speed would be 6 meters per second. I know this is speed because it's meters per second. And notice that the slope is constant, right? So on a line, the slope is constant. All right. So first, let's explore graphing motion with an app. All right. So let me just find the right one for us. All right, so let's look at constant velocity. A blue car that's going to be at rest, and we're going to have a red car that's traveling at 5 meters per second, at a constant 5 meters per second. And we're graphing position versus time. And we're going to look at the dot diagrams, and we're going to look at the position graph. So if it's just staying at rest, the blue car literally just has one dot at one location. And the red car is equally spaced dots that are 5 meters apart every second. If we were to make this a graph of distance versus time, you would see that the slope of this, and let's pick 2 points. We could pick this point and we could pick the 100-meter point in 20 seconds. The slope, the rise would be 100 meters and the slope would be 20 seconds. And so that would turn out to be 5 meters per second. Notice that on our dot diagram, the red dot is equally spaced, and it is increasing its distance 5 meters every second. Notice that for the blue car, this is sitting still, it sits at 0 meters the whole time. So a linear graph on a position graph means that the object is traveling at a constant speed. What happens if we start to accelerate? So let's give it an acceleration of 2 meters per second. And let's look at car 2 versus car 1, who's traveling at a constant speed. Notice that the dot diagram gets bigger and bigger to the right. And notice what happens. The slope of the graph changes. It gets steeper and steeper. So a position graph, the slope of the position graph is speed. If the speed is constant, it will be a linear graph. If the speed is 0, it will be a flat graph. If the speed changes, its slope will change accordingly. So then, since this was moving to the right, its velocity is positive, which means its slope is positive, but the slope is increasing every instant in time, so it becomes parabolic. So a parabolic position graph means acceleration. So let's just summarize that. If we have an xt graph that is flat, it's at rest. If we have an xt graph that is linear, it's traveling at constant speed, and the slope is equal to its speed. And if we have a graph that's parabolic, right, the slope in this case is increasing, so it's speeding up. It's constant acceleration. It has a changing slope. We could be getting slower if we wanted to, right? And if that were the case, we'd start out steep and then we would get flatter. So the big deal is that on a position graph, slope is speed. If it's a positive slope, you're going away from the start point. If it's a negative slope, you're going towards the start point. So let's practice. Let's find the slope, the speed, the average speed from 0 to 10 seconds. So what we're really going to do is we're going to find the total distance, right? So it started at 0, and at 10, it went up to 60. So really what we're doing is we're finding, when we find the average speed, we're finding the slope between 2 points. It would be 60 meters divided by, oops, I think I drew that the wrong way. Actually, I wanted to find the total speed for 15 seconds. I'm sorry, for 15 seconds. So the average speed would be 60 divided by 15, which is 4 meters per second. Okay. The average velocity would be the total displacement all over the total time. Well, the displacement is positive 60 meters in 15 seconds, so the total average velocity is positive 4 meters per second. What if I wanted to know the instantaneous speed at 12 seconds? At 12 seconds, right here, would be the slope at that instant. So the speed at 12 is 0, and so is the velocity at that instant. What if I wanted to know the direction that it was traveling at 30 seconds? Well, the direction that it's traveling at would be negative. So it would be to the right, to the left, or down, depending on the actual context of the problem. The instantaneous speed would be just a slope at that instant. What is the instantaneous speed at 40 seconds? What's the slope at that instant, which is 0? What is the instantaneous speed at 35 seconds? It would be the slope of that big line, whatever that line is at that instant. So let's label and describe what's going on in these graphs. First of all, the slope is not constant. So these are all undergoing some kind of constant acceleration. That's the type of motion. Let's really talk about what's going on. The slope is getting steeper, so it's moving in a positive direction, and the slope is getting flatter. It's slowing down. In this case, it starts out really steep, and it's negative. So it's moving in a negative direction, but it's slowing down because the slope is getting flatter once again. Slope is getting flatter. What's happening to the slope here? You start out pretty flat and then you get steeper and steeper. So if you're getting steeper, you're getting faster. And it has a negative direction of motion. So it's moving to the west. And then here, you're getting steeper and steeper and steeper. So you're once again getting faster. But you're going to a positive direction. So increasing slope equals increasing speed. Decreasing slope indicates decreasing speed. You're slowing down.